A 24 volt, 1 horsepower DC motor that is 90% efficient requires how much power to run? Okay, so we have our motor here. I just drew a small diagram. This is the motor, and whenever it's saying the motor has a 1 horsepower rating, what they're saying is the shaft of the motor turns with mechanical power of 1 horsepower. So whenever you buy a motor, if it says that the motor is 1 horsepower motor, that means it will turn the shaft with 1 horsepower of power. It doesn't matter the efficiency of the motor, the shaft will turn with that much power, whatever it's rated at. So what is the efficiency then of a motor? Well, let's just look at this real quick. So what we often do when we're doing these problems is we're converting this mechanical power to electrical power. So let's just go ahead and do that right off the bat. So we do know that 1 horsepower is equal to 746 watts. So we know that this 1 horsepower, if we convert it to electrical power, is 746 watts. So those are one and the same. So the shaft turns with 746 watts of power. So what does that mean as far as it means for efficiency, right? So this just means a motor's efficiency is how much power is going to be required to run the motor. So the battery is supplying current, right? And it has a voltage, so we know that there's a power being produced here, because we know that power is equal to current times voltage. We're not asked to find the current in this problem or anything, but the idea is this side, the input is electrical power. The output is mechanical power. We know that our output is 746 watts. So the closer that we get to being 100%, you're not going to have a 100% efficiency motor. That would mean if it was 100% efficiency, that would mean it'd take 746 watts to run this motor and get out 746 watts of power. And that's just impossible. There's going to be losses. You're going to have friction and bearings in the motor. There's going to be losses in the electromagnetic field that you need to run this motor. Regardless, that the closer it is to 100, the closer it will be to the output power. If it has a really low efficiency, that means it takes a lot of power to run this motor compared to what you're getting out of the motor. So again, for this problem, we do have to know the equation. Efficiency is equal to output power over input power. So if we always know our input power is going to be larger than our output power, that means in this fraction, because that's what this is, a fraction here, our denominator is always going to be larger than our numerator. The bottom is always going to be larger than the top. Therefore, this will never be over 1, or it will always be a decimal. So it will never be 100%. It will never be over 100%. If you get 1 point something somehow, you've done something wrong. Okay, so let's just go ahead and solve this problem. So we do know the efficiency, so we need to use that. So we have our efficiency is equal to 90%. Let's go ahead and just convert it to a decimal. So not 0.9 or 0.90. And we do know our motor's output, right? That goes in the top. So we have our output is 746. I'm just going to leave the unit off for now, but it's watts. And what we don't know is our input. So I'm just going to write it as a lowercase I, so I don't have to move it around. So then we just come to the simple algebra equation. So we just need to solve for I. So we're going to multiply both sides by I. I divided by I is 1. Anything divided by itself is 1. So we're left with 0.90 I equals 746. Then we're going to divide by 0.90, divide by 0.90, and I, or the input power, this part here, the input power, is equal to 828 watts.